Hey guys, how you doing? It's Coach Scott. Let's do the last video in our series on intermolecular forces and state changes. So let's talk about solids real quick. All right. So there are two types of solids, two main types for the most part that we're going to experience. One is an amorphous solid, right? Notice there's no rhyme or reason, no particular order on how these particles are arranged, right? The other one would what we call a crystalline solid. Now, crystalline solids have a very orderly arrangement. You see, these are nice little hexagons, and if you added more, they would be like this. So, uh, amorphous solids, and I used to deal a lot with those when I was in industry. Amorphous solids are like your rubber, most plastics, glass, paraffin wax, candy. All right. Crystalline solids are ionic compounds, metals, and covalent network solids. All right. Uh, Crystalline solids are characterized by the bonding type, as we're going to see this in the next little slide. So, if you have a molecular crystalline solid, you've got atoms or molecules. The forces would be LDFs, dipole-dipole hydrogen bonds. They're very hard and brittle, low melting point, poor thermal and electrical conduction. So this would be like sugar, carbon dioxide, argon, methane. So yeah, those would be molecular crystalline solids. Covalent network solids, atoms, they're atoms. They're covalently bonded. Now these guys are fairly soft. They have low to moderately high melting point and very poor thermal and electrical conductivity. Think diamond, think quartz, silicon dioxide. Yeah. Ionic crystalline solids or ionic solids are positive and negative ions. They're charged and attract to each other. They have Coulombic attractions. All right. Very hard, very high melting points. It depends on whether they're good thermal or electrical conductors. Think about these are salts like sodium chloride, potassium chloride, sodium fluoride, so on and so forth. Metallic solids. Now they're also atoms. They're held together by metallic bonds. Those are the forces holding them together. That sea of electrons. They're usually soft or can be very hard. They have low to very high melting point, excellent thermal, electrical, and electrical conduction. All right, they're very malleable. They're very ductile. Think all of your metallic elements: copper, iron, aluminum, potassium, things like that. Okay, they're going to have metallic bonds. So let's talk about diamonds real quick. Diamonds are a good example of a covalent network solid. Now, these carbon atoms are covalently bonded to four other carbon atoms. These guys tend to have very hard and have very high melting points. It'd be extremely hard to melt a diamond. It can be done, but it would be very hard. Now let's look at another allotrope of carbon. All right, graphite is another example. It's carbon, right, of a covalent network solid. Now these guys, carbon atoms in graphite, they're bonded to three others, and then they're bonded or they're in layers of interconnected hexagonal rings, like so. So the carbons are covalently bonded to three or three other carbons, okay, and then they're layered on top of each other. Now these are held together. The layers are held together not by a covalent bond, but by LDFs or weak dispersion forces. This allows them to slide easily across one another. So graphite is an excellent dry lubricant and also very good as the lead in pencils because those layers can move off of the tip of the graphite into the paper. Pretty cool. Now metallic solids. Now these are not covalently bonded, all right? And these attractions are all, between the atoms are way too strong for intermolecular force. So in metals, these valence electrons are delocalized, the outer electrons, are delocalized. They're not owned by any one atom. So these will move around freely around all of the nuclei. And we're only talking about the valence electrons. So the delocalized nature of the electrons account for many of their physical properties. So metals are pretty good conductors of heat and electricity because those electrons can move around the solid. They're very malleable and very ductile, which means they can be drawn into wires, or I can beat them down flat. Now, glass is made by melting a mixture of sand and other minerals and salts in a furnace at around 1800 degrees C. That's hot. Now, lightning can also fuse sand, and they even found glass in the sands of the New Mexico desert where they exploded atomic bombs. They were doing testing like that. They would find this glass made because it got so dang hot. All right, so let's move on to properties of matter. So, metals are lustrous. Gold is a soft metal. It's non-reactive, solid at a room temperature. Salt water is transparent, or what we call water white. It's a liquid at room temperature. It can be separated by heat, no definite composition. Pure water is transparent or water white, liquid at room temperature. It has a definite composition. It can only be separated by electrolysis into the hydrogen and oxygen atoms. Calcium carbonate, all right, is a solid at room temperature, has a very high melting point, is non-lustrous, and it could be separated by heat. Now, we're just talking about the physical properties of some stuff. So a physical property is a characteristic that can be observed without altering what that material is. So let's talk about some of the physical properties of water, or let's describe water. So we know water melts at 0 degrees Celsius at standard pressure. Water is transparent, or most people call that water white. Water has a density of roughly 1 gram per milliliter at 25 degrees C. It is not soluble in gasoline and other nonpolar solvents. Water is colorless. All right. Now, these are all properties that we can just look at some water and tell it's still going to be water, whatever water you get. All right. Now, let's talk about a brick oven pizza. What makes a brick oven? Bricks. So the bricks that make this oven are made of a mixture of aluminum oxide and silicon oxide. Now, think about some of the physical properties of the brick that you can feel. All right, now let's think about it. A brick is hard. It's pretty dense, very brittle. You can break a brick with a hammer. Right. So that's a brick. Right. So chemical changes result in a new substance. Like if we burn something, we can bust it. We can oxidize something or rust it. We can decompose something, split it apart. Now, physical changes don't change what the substance is. So we can talk about changes of state, changes of temperature. We can heat something up, cool it down, measure the volume, so on and so forth. That's the physical change. Right? We're not really changing what it is. So when we have changed the identity of the material, we can see some things that makes us know that it's changed. One is the color change, when light is emitted, when a precipitate is formed, or when a gas is formed. These are considered changes of a chemical of changes the chemical properties of what that substance is, right? So when I burn a marshmallow, I go for that white gooey deliciousness into a dark, crispy, caramelized coating. I've changed something. When I burn wood, I'm going to wood into flame, putting off smoke, and making it into an ash. So I'm changing what it is. When I take two liquids together and I form something yellow and clear liquid, then I've made a precipitate or a solid from two liquids. When I heat up limestone, I'll produce a gas. So, in your own mind, talk about the different properties of a delicious pepperoni pizza and the oven that it's made in. You guys think about it and talk about it. So, let's think about this. When I make a burger, right, I can melt that burger or melt that cheese I put on that cheeseburger, or I can burn it. Now, one of those is a chemical change and one is a physical change. Which is what? Well, if my cheese turns dark, okay, I've burned it. When I melt it and it starts to flow over the burger, then I've changed the physical state of the cheese. So, extensive properties of matter are properties in which the value depends on how much of the material is present. So, mass, if I've got a lot of something, a lot of stuff there, okay, then the mass of a glass of water is 30 grams. I could add more water to that glass and then it would increase the mass. So it depends on how much of the water is there. If I have a stick and I'm measuring it's 12.2 meters, well, I could tie on another piece of the stick and I can lengthen it or I can cut the stick in two. So the length depends on how much of the thing is there. If I have a balloon and I say I have 14.7 liters of gas in there, okay, I can add more gas, blow the balloon up, and I've increased the volume. So these are extensive properties of matter. Depends on how much is there. Now, intensive properties doesn't matter on how much of the stuff is there. Water is transparent. It's colorless, or we do call it water white. The melting point, if I have a little chunk of iron, or if I have a big chunk of iron, or a big rock of iron, it's still going to melt at 1538 Celsius. Now, the specific heat of aluminum is always going to be 0.89. It does not matter if I have 100 grams of aluminum or 10 grams of aluminum. The specific heat is still going to be 0.89 joules per gram Celsius. So, density is a perfect example of what an intensive property is. It doesn't matter the size of the sample. The ratio of mass to volume of a substance is always going to be the same. Now, if I have more volume of the sample, guess what? The mass will also be higher. All right? So any type of difference here is, well, that's from experimental error, measurement error, that's all. So we'll talk about this in class. Some meteorites found on the Earth's surface are made of solid metal like iron. So what kind of property, intensive or extensive, do you think would be most useful in identifying the metal in the meteorite? Think about that. So this is a good summary of the properties of matter. A physical property you can observe without changing what the stuff is. Now think melting point, density, color, solubility, hardness. This lets us determine what the stuff is. Then you're going to have, it's going to break away into intensive properties and extensive properties. Intensive, it doesn't matter how much is there. All right. These are things like color, melting point, density. All right. Doesn't matter how much stuff is there. Extensive depends on how much is there. This is stuff like mass, length, volume, so on and so forth. Now, a chemical property can be observed by changing the identity of the substance. And one of these would be like reactivity with other substances. So guys, this concludes our states of matter, properties of metals, and our unit on IMFs. So hopefully we learned something a little new. And so, anyway, this is Coach Scott saying, deuces.